Hello everyone. I hope Hello everyone. I hope I'm audible and my screen is also I hope clearly visible. So this is let's begin this today's tutorial session. This is tutorial 6 of the NPTEL course Linear Algebra, and the course faculty is Dilip Patel, and let's begin the course begin this tutorial session. Okay. So this is tutorial 6. Tutorial 6 Linear Algebra. This is an NPTEL course. The course code is, and today is 28th August. Okay, so mostly today we'll discuss some problems. We'll discuss some problems regarding the linear transformation on a vector space. So let's begin with the what is we mean by linear transformation and what are the application of those linear transformations. So in today's tutorial session, so mostly we'll discuss some notion of the linear transformation between two vector space and their applications mostly. Okay, so 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 let's begin with the definition of the linear transformation. Let V and W, let V, W are two K vector space. That means they are vector space over the field K. Okay, this we can consider K is real or complex number. That's complex number space. That's what it is. Then a map if from V to W is said to be linear transformation or K-linear map if it satisfies the condition that f of C alpha plus beta is equals to C of f alpha plus f beta for all scalars C coming from the field K and alpha beta coming from the vector space V. Then we say f is K-linear map. So if we this is what it is. Now the main point what is the importance of a linear transformation? What is the importance of a linear transformation or linear map, K-linear map? Why one should study a K-linear map? And why that is related with the vector space? And this is also sometimes called K-linear homomorphism. Okay, between two vector space V and W. So, I mean, we can study just a map. F is a map from V to W. That is a function that sends every element in V to another element in W. But why one should study the linear transformation? Because if V is a finite dimensional vector space, V is a finite dimensional vector space with dimension. Let's take dimension of V is equals to n, and let's take that alpha 1 all the way alpha n is a basis of the vector space V. We have discussed what is basis of a vector space. That is a linearly independent set whose spans the space V. Okay, that is, then for any alpha belongs to the vector space V, there exists some scalar C1, C2, Cn, and they are unique in fact, coming from the field K, such that alpha can be written as C1 alpha 1 plus all the way Cn alpha n. Here Ci's are unique. Whenever we are considering the fixed orthonormal fixed vector space, fixed basis alpha and alpha. So now, what is the importance of the linear transformation? So what we have this property that f is a linear transformation, then it will satisfy. If f is a linear transformation, then it will satisfy this relation that f of C alpha plus beta is equals to C F alpha plus F beta for all scalar C coming from the field K and all alpha beta vector coming from the um, vector space V. So, so what is the importance that if we take any arbitrary vector alpha in V, then we will have this type of linear combination of the elements. Then f of alpha, that has to be f of C1 alpha 1 plus all the way Cn alpha n. That means if we use this rule of the linear transformation, that is it satisfies this condition, then I will get that C1 f of alpha 1 plus all the way Cn f of alpha n. So that means if I want to know what is f of alpha, then it is enough to know what is f of alpha 1, what is f of alpha n, what is f of alpha 2 and all this. So that is to know f of alpha, it is enough to know f of alpha 1 all the way f of alpha n. That is what is the main fact is that when you have when you have just an arbitrary function between two set x and y, and you want to know what is the function, you should know the value of the function f at each point of the set x, right? But here f being a linear transformation, that is a map given by this way. Just a minute. So which is given by this property, which satisfies this property, then V being a vector space, every element can be written like this way. Then f of alpha can be written like this way. That means if we know what is f of alpha 1, what is f of alpha 2, what is f of alpha, then we know what is f of alpha. So the advantage is that if V is a vector space and f is a linear transformation from the vector space V, then what is the advantage? What is the advantage we are getting if we know the value of the function f on an basis, that is alpha 1, alpha 2, alpha n, or any basis, then we know the value of the function on every element by taking this type of linear combination. Okay, that's the importance of linear transformation. But here I'll just take one more point. So whenever, now this is what is called linear transformation and what is the importance of linear transformation. This is what it is. Next point is that when we say the linear transformation is injective, the linear transformation note that linear transformation can be said as the K-linear map or K-linear homomorphism, anything. Linear transformation F is said to be injective or 1-1 or 1-1 if f of alpha is equals to 0, implies that alpha is equals to 0 for any alpha belongs to the vector space V. If we start any vector alpha coming from the vector space V, or you can write if for any, something like I have written little other way, if for any alpha coming from the vector space V, f of alpha is equals to 0, then we should have alpha is equals to 0. This is called injective, and we know that injective by 1-1. This is called 1-1. Okay, the linear transformation if is said to be surjective if for any vector w in the vector space W there exists and vector alpha in coming from or V coming from the vector space V such that f of V is equal to W. F of V is equal to this small w. So the main point is that if you take any vector, f is a linear transformation from the vector space V to V, from V to W, then for every vector f there exists a pre-image, then we say that f is surjective. But there can, for a fixed element W in capital W, there can have more than one pre-image. Okay, that can happen. Okay, so f is said to be isomorphism. The linear transformation f is said to be isomorphism if it is both injective and surjective. That is called bijective. Okay, the f is said to be uh, f is said to be isomorphism if f is both injective, of course linear, f is linear, injective and surjective. So the linear transformation, the linear transformation. In that case, if V and W are two vector space, in that case, if V and W are two vector space over a field K, and if from V to W be an isomorphism, that means a linear map, linear transformation, and that is also both injective and surjective. Then V and W are said to be isomorphic. Okay. This is what called isomorphism, and whenever we have an isomorphism in between two vector space, then we say those two vector spaces are isomorphic. So here is an interesting fact, uh, that is, let V be a finite dimensional vector space over a field K, and let's take dimension of V is equals to n, and let W be another vector space and F from V to W be a linear map. So here, if F is injective, I mean linear and injective, then dimension of W, that must be greater than equals to n. What is mean by this? This means W contains more than n linearly independent vectors. Why this happens? So suppose F is injective and V is a finite dimensional vector space of dimension n. Let beta is equal to something like alpha 1, alpha 2, alpha n be a basis of V. So the basis means that every vector in vector space V can be written as linear combination of those vectors, and that is also unique. But the most important point is that okay, that spans, then that is linearly independent and spans the set. Okay, then f of then claim, I'm claiming that, then if then claim is then claim is if f is injective, which I have assumed, then f of alpha 1 all the way f of alpha n is linearly independent. This is linearly independent as a elements in the vector as in elements in the vector space W. Okay, they belong in the vector space W. They no longer belong in the vector space B. Is linearly independent. Why this happens? Let's try to prove this. Let's f1 plus all the way c and f of alpha n, this is equal to 0. If this happens, then we know the f being linear, I can write it as c or alpha 1 plus all the way c and alpha n is equal to 0. But what we have said, that f is injective. This happens because as f is linear transformation. Now, then from here what we'll get, as f is injective, I will get c alpha 1 plus all the way plus c n alpha n equals to 0. This happens as f is injective. So f is injective means what I have said, if of f of alpha is equal to 0, then f of alpha is equal to 0, that implies alpha is equal to 0. This is what it is injective, but this fact is equivalent, that if f of alpha 1 is equals to f of alpha 2, that implies alpha 1 is equals to alpha 2. Why that happens? Because as f being linear, we can write f of alpha 1 minus f of alpha 2 is equals to 0. F is linear, and this is nothing but f of alpha 1 minus alpha 2. So now, as if I assume this definition, that f of alpha is equals to 0 should imply alpha equals to 0, that as the definition of linearity, injectivity, then this, if we know this fact, then we can write alpha 1 minus alpha 2 is equals to 0. That means alpha 1 equals to alpha 2. That's vector space property, all these things. Converse is also similar. Okay. So this happens, but we know that alpha and alpha to alpha n are linearly independent because that is a basis. So this will give C1 equals to C2 equals to all the way Cn is equals to 0. This happens as the set alpha and alpha to alpha n is basis of V. So in particular, they are linearly independent. So what we obtained that if we take alpha and alpha to alpha n as an element in the vector space V, I mean as an basis in the vector space V, then f of alpha and alpha to alpha n are linearly independent. That's what we got. And we know a vector space can have, I mean, if the dimension of a vector space is always is equal to the number of, here I can write dimension of a vector space is equal, this fact you can write, equal to the number of maximum number of linearly independent maximum number of elements, maximum possible number of elements in a linearly independent set. Possible number of elements in a linearly independent sets. That means there can be many linearly independent sets. Okay, the dimension of a vector space will be the maximum number. I mean, you can get many linearly independent sets. The sets which contains the maximum number of linearly independent vectors, that will be the basis, and that number of the element of that set is called the number of element of that set is called the dimension of the vector space V. In fact, if you take a vector space V and you take, you know that the maximum number of linearly independent elements in a set of that vector space can have n. I mean, suppose you have vector space W and you are taking two set S1, S2, and you know that whatever subset you choose from W, the number of maximum linearly independent set only possible is n. That means if we choose such two set S1, S2 for which we have n number of linearly independent vectors, in that situation both of them will be basis of the vector space V. Okay. If you, I know these facts are not that much trivial, but if you have any, I mean, I can't prove everything, but if you still interested, then you can let me know. I'll try to prove this. Okay. But I'll use these facts, so that's why I'm mentioning this. Okay. So what I'm getting here, so here we have the n number of linearly independent vectors in the vector space V, a vector space W. So that implies dimension of W must be greater than equals to n, as the space W contains n number of linearly independent set vectors. It contains a set of vectors which contains n number of linearly independent vectors. So that means whatever the basis it will contain, that basis will have more than this number of linearly independent vectors. So that's why the dimension of W is always greater than equals to n. Okay. Now another fact is that what I have said, when f is surjective, f is injective. If f is surjective, then what we can say? Then we know that for every W belongs to capital W, there exists a vector V in capital V such that f of V is equals to W. Also, with the fact that f is linear transformation. If in the situation W is a finite dimensional vector space of dimension m with an basis beta 1 all the way beta m, in that situation, or w1 all the way wn, no, beta 1 beta 2 beta 1, let's see, beta 1 all the way beta m, then f inverse of beta 1 beta I, that will contain in V. That means there exists a vector, that is what it is. If that means there exists a vector, that means there exists a vector alpha I coming from the vector space V, such that f of alpha I equals to beta I, okay, for all I equals to 1 to n. Now, as beta 1 to beta m are linearly independent, and no, we can't say anything here. This is linearly independent. If it is injective only, then okay, we can't say anything. Okay, no, here we can't say anything. Here we can't say anything. But what we can say is that let's take V is a finite dimensional vector space, and we have two facts. We have know what is the bijectiveness. Bijectiveness is that vector space V, bijectiveness, that is injective and surjective, and linearity needs necessity. That is. Now if V and W are finite dimensional vector space of same dimension n, and if from V to W be a linear transformation, then if F is injective, then F is injective, then F is surjective. F is surjective, that implies F is bijective. Okay, these two factors same. If F is injective, then F is surjective or F is bijective. That because injective surjective is both there, then it will be bijective. And another fact is that then V and W are isomorphic. Why? When V and W should have the same dimension in that situation only. Okay, because as we have said, as I have said that if V has a basis, like let's take V has the basis alpha 1 alpha 2 alpha n, then for every vector, then f of alpha 1 all the way f of alpha n, this is a linearly independent set, is because f is injective, is a linearly independent set, linearly independent set, and then this set f of alpha 1 alpha 2 alpha n, this is a basis of W, because W has dimension n and we got a linearly independent set of n vectors, then that set has to be basis. There is no other way. Okay. So then why F is surjective? Because if I take any W coming from the vector space W, then W can be written as summation of Ci f of alpha I for I equals to 1 to n, because this is the basis set. Now this can be written as F is linear, this can be written as Ci alpha I equals to 1 to n. This is what it is. Okay, so that means this element is automatically coming from the vector space V. That means for every W, I got an element V where V is equals to summation of Ci alpha I equals to 1 to n, such that f of V is equals to W. That is, f is surjective. Similarly, if V and W are finite dimensional vector space of same dimension over the same field, that is very necessity. To define a linear transformation, we always need the two vector space has to be defined over the same field. Okay, of same dimension n, then if from V to W be a linear transformation that is surjective, then F is bijective. That means what I have to prove? I have to prove that that if F is a linear transformation from V to W and F is surjective, then I have to prove that F is bijective. Okay. So why this has to be bijective? So basically, what I have to prove that F is injective. That is, we need to prove F is injective. This is what it is, right? Because linearity is there, everything is there. What is we mean by injectivity? Either f of alpha 1 equals to f of alpha 2 implies alpha 1 equals to alpha 2, or f of alpha is equals to 0 should imply alpha is equals to 0. This is what it is mean by injectivity. But how I will prove that? Let's look at the things. Let's beta 1 all the way beta n. Let beta 1 to beta n is a basis of the vector space V. As f is surjective, there exist alpha 1 to alpha n vectors coming from the vector space V, such that f of alpha I such that f of alpha I is equals to beta I. Okay, for all I equals to 1 to n, that should happen. Okay, there exists alpha 1, alpha 2, alpha n. Now my claim is that this alpha 1 to alpha 1, alpha 2, alpha n are linearly independent. This is what it is I want to prove there. Claim alpha 1 are linearly independent. If not, there exists some C1, C2, Cn, not all of them, 0, not all of, that's okay, claim is this, so let's try to prove this one. Summation of, so let's take summation of Ci alpha is equals to 0. Then what I have to prove that f is 0. Okay, here is very important point what I have missed to state, that if f is a linear transformation, then that always map f of 0 to 0. That is very much clear. Why that is clear? Because if you take alpha is a vector and let's take c is equals to 0 and beta is equals to 0 vector, alpha any vector, okay, then what will happen? Then f of this will be 0, right? Because c is 0, alpha is some vector that can be 0, non-zero, but beta is 0. That means that can be written as, okay, what I want to prove, that f of 0 is equals to 0, right? That is what it is I want to prove. Okay, so sorry, I should not do this. This is not the correct way. So let's take f of 0, 0. This can be written as f of alpha minus alpha. Okay. Now due to linearity, we can write f of alpha minus f of alpha, that is equals to 0. That's why f of 0 is equals to 0. That means a linear map always maps 0 to 0. Okay. Linear transformation always maps 0 to 0. From here to here, we are using the linearity. Okay. And here we know that alpha minus alpha is equals to 0. That we know if alpha is a non-zero vector, in the vector space V, then we will have this fact. Okay. There is a many way one can prove. One of the other way is that f of 0 can be written as f of 0 plus 0. That can be written as f of 0 plus f of 0, and this will give that f of 0 is equals to 0. This will also give. Okay. So this way one can prove. Okay. So linear transformation always maps 0 to 0. This is what it is my point. Okay. So if I assume these elements equals to 0, then to prove alpha 1, alpha 2, alpha n is linearly independent. If it is linearly independent, if I can prove this is linearly independent, then as if this set has n number of elements and the vector space V, by the assumption, has the same dimension with n, that is same dimension with W, that is n, then then this set will form a basis of the vector space V. But anyway, but I don't need those facts. But let's see. If this equals to 0, then I have to prove that all the Ci is equals to 0. That's I have to prove. But we can get that summation of Ci alpha I is equals to f of 0. F being a linear transformation, this is 0. Now f being a linear map, we can write f of alpha I equals to 0. But we know that f of alpha I is nothing but c of beta I. And this is 0, I equals to 1 to n. But as beta 1 to beta n are bases, then what we can get, that all the C1, C2, all this has to be 0. So this says this alpha 1, alpha 2, alpha n, which are actually inverse image of beta 1, beta 2, beta n, under the condition that f is surjective, this is a basis of the vector space of the vector space V. Okay. But what I want to prove? I want to prove that f is injective. Okay. F is injective. That means if f of alpha is equals to 0, then alpha has to be 0. So how I can prove? Let's take alpha is a vector in V. As this is a basis under the condition that this is surjective, then alpha can be written as summation of Ci alpha. Now let's take, let f of alpha is equals to 0. That means f of summation of Ci alpha is equals to 0. That says Ci summation of Ci f of alpha I is equals to 0. That gives the same argument I am talking about, that all the Ci is equal to 0 for all I equals to 1 to n, and whenever all the Ci are 0, that gives alpha is equals to 0. That what I have proved. That if f of alpha is equals to 0, alpha I have started with any vector. So as alpha is an arbitrary vector in the vector space V, and alpha 1, alpha 2, alpha n are bases of the vector space V, then alpha can be written linear combination of this for some C1, C2 all the way Cn coming from the field K. Okay, this is what it is. So this is then alpha has to be this from alpha. I mean alpha has to be 0. This is what it is. Now, so that means what we obtained, that is alpha, that is f is injective. So if we have a linear transformation between two finite dimensional vector space with the same dimension, then just only having one, that is injective, that will give surjective. If we have surjective, that will give injective. Okay. One more fact is there which I am not going to prove. If that is using, then I will prove that time. If f is a linear transformation that is bijective, at least injective. Another fact is that if f is injective or biject, if is injective, then that we have proved. If it is injective, then f sends a linear or sends a. We have observed. So let me clearly mention it. We have observed that if f is a injective linear map, injective linear transformation, then f maps and basis, a basis to a basis, a basis, a linearly independent set, linearly independent set to to a linearly independent set. Right, that what we have observed. But the point is that if we have a map F that sends every linearly independent map to every linearly independent set to a linearly independent set, then that function has to be injective. Conversely, if f is a linear transformation from V to W, be a linear transformation that maps every linearly independent set to a linearly independent set, then f is injective. Why f is injective? Let's take f of alpha is equals to 0. Then claim is alpha is 0, right? That's what it is I have to prove. If alpha is not equals to 0, then what I can write? Yeah, f has to be, if this is done because, okay, here is a fact. The set, any set which contains 0, that is linearly dependent. Any set of a vector space which contains zero element of the vector space must be linearly dependent. So that what I am trying to say is that if you are taking a set of a vector space V and that set contains the 0 vector, then that set is always linearly dependent. Whatever vector is there doesn't matter, because you can write scalar, you can multiply to the 0 by a non-zero scalar and still you get the 0. That's why it is 0. So now as 0 is a linearly dependent set, then the vector alpha itself is a linearly dependent set in the vector space V. But if a singleton set linearly dependent can happens only when the vector itself is zero. That is alpha is equals to zero. Because if alpha is not equals to zero, then you can't multiply any non-zero scalar C to alpha to get zero. You can't do that. If we have C non-zero entry and alpha is non-zero, alpha is also not equals to zero, then you can't get this. You can't get any way that C of alpha is equals to zero. So there, if that means the set alpha has to be zero, because if C alpha is equals to zero, then there is an alpha not equals to zero, then there is only way this product can be zero, that is C equals to zero, right? This scalar multiplication can be zero if C equals to zero. This is what it is. Singleton set is this, what it is this. Okay, so F is injective. That says F is injective. So we have done enough theorem, so let's go to some problem. Let's see if we can do something. I hope my screen is visible. So here few of them, I'll check here the linearity of this map. I hope it is. Okay, let's see. Okay, so we'll check the linearity of this, some few of the map. Okay, so let's take this map. F is the map R square to R square. Okay, given by f of x1 x2 is equals to x1 square x2. Whether this map is linear or not. Here is a golden rule. Whenever you have square, there is a very high chance that that map is not linear. Let's see why I am saying this. F of x1, so map is f of x1 x2 is equals to f of x1 is equals to x1 square x2. This is what it is, the map. Okay, so I have to prove that to linearity. I have to prove that f of c alpha plus beta that happens. If that does not happen anyway, then we will say that okay, this can happen. Okay, so let's see. If we write 1, so what it is mapping? F10 is equals to 1 comma 0. F2 comma 0, that going to be 2 square comma 0, that is nothing but 4 comma 0. But f of 1 comma 0 plus 2 comma 0, that should satisfy if it is linear. That's okay. Let me calculate this. This one, what it is? It is supposed to be 9 comma 0. That is what it is. But if it is linear, then what it should happen? It should happen 1 comma 0 plus f of 2 comma 0, and which is equals to 1 comma 0 is 1 0, 2 comma 0 is 4 comma 0, and which is equals to 5 comma 0, and this is not equals to this fact. Okay, 9 comma 0 is not equals to 5 comma 0. So that's why f is not linear. Similarly, if we consider some other this type of, if we have a square, what I have said, if you have a square, then then the function need not be linear. And similarly, if you have some scalar something like that, addition like this plus one, in that situation also the function need not be. In that situation also function need not be. In fact, in that situation function is not linear. Why I am saying this? Let's see why I am saying this. So let's take the function 2 that says f of x1 x2 is equals to x1 plus 1 comma 0. So that means f of 0 comma 0 that goes 1 comma 0, f of 1 comma 0 that goes 2 comma 0. So by the rules, f of 0 comma 0 plus 1 comma 0, this has to be f of 1 comma 0, as this is what it is 7, so it has to be 2 comma 0. But if it is linear, then it should be 0 comma f of 0 comma 0, f of 1 comma 0, which is supposed to be 1 comma 0 plus 2 comma 0, and which is equals to 3 comma 0, and these two are not equal. So that's why it is also, so f is also not linear. So let's check another For in this situation, this may be linear. So let's check. F of x1, x2, x3 is equals to 3x1 plus 2x2, x1 plus x3. So F from map from R cube, R3 to R square, both are vector space over the field R. Okay, R is the real field, and giving by the function F x1, x2, x3 that is equals to 3x1 plus 2x2, comma 3x1 plus 2x2 plus x1 plus x3. I hope I have written correctly. Let me 3x1 plus x2, x1 plus x3. Yeah, I have written correctly. So here to prove. So whenever I am trying to prove that a vector, a function is linear transformation or not. That I'm giving. If it is not, then we are giving a counter example. We are giving some pairs for which it is not satisfying the linearity. But whenever we want to prove the linearity, we have to give the full proof. So let's take two vector alpha which is equals to x1, x2, x3, another vector beta which is equals to y1, y2, y2, y3, and they are coming from the vector space R3. Let's take C is a element that is coming from R, that is scalar. In that situation, I have to prove that f of C alpha plus beta is equal to C of f alpha plus beta. So this can be written as Cx1, directly I am writing y1, comma Cx2 plus y2, Cx3 plus y3, and this is by the rules 3 of Cx1 plus y1 plus, this is what it is, plus 2 of x2, that is Cx2 plus y2, comma, this is the first entry, and another entry is x1, that is Cx1 plus y1 plus x3, that is Cx3 plus y3. Okay, now this can be written as, so what I want to prove that, I want to prove that C of f alpha plus f beta, that is what it is I want to prove. So let's separate C and then I'll get whatever we want to get. Okay, so what I can write, I can write this as Cx1, let's take all the C entries, plus 2x2, comma, if I take from here, this will be x1 plus x3, plus this will be 3y1 plus 2y2, comma, y1 plus y3. You can very carefully check if this is correct. So then this will be C of f of x1, x2, x3, plus this will be f of y1, y2, y3. So that says this is nothing but C of alpha, f of beta. Okay, this says f is linear. And one more fact here I have, when I'm trying to say whether this is a linear transformation or not, here is a very interesting fact. One fact I have tried to prove that here f of 0, that is equals to 1 comma 0, which is not equals to 0 comma 0. One thing I have mentioned when I am trying to give the, say what is linear transformation, that if f is a linear transformation, then that should map the 0 entry to 0, I mean 0 vector to the 0 vector. But here it is mapping 0 vector to 1 comma 0, which is not a 0 vector in R2. So that's why this is not a linear transformation. So you can directly check using that one. But you can't use that check here. I mean, this is not linear, but you can't discard or you can't prove that this is not linear by using that fact that f of 0 is not equals to 0 comma 0. Here it is f of 0 equals to 0 comma 0. Still, it is not a linear functional. So that means a linear functional always maps 0 to 0, 0 vector to 0 vector. But if a function that just only maps 0 vector to 0 vector, that does not guarantee that is a linear transformation. Okay, we have to prove that all the main property. We have to satisfy this main property, that f of C alpha plus beta is equal to C of f alpha plus f beta. Okay, I hope this is clear. Okay, so next problem, before going to the next problem, I just want to recall a few facts. No, we don't need to give any facts. Okay, let's go to the next problem. I hope it is clear. If there is any doubt, anything you want to know from your side, you can you can ask me. I'll try to explain. Any questions arises to you from the lectures, videos, or my tutorial session, or any things which come through which came in front of you regarding this tutorial linear algebra course, you can ask me. I'll try to discuss or try to solve those problems. Okay, and even those problems which I am discussing here, even still there is any doubt in this problem, still you can ask me. I'll try to discuss this problem. Even if I am doing something, you can stop me and I'll try to discuss this problem. Okay, so let's go to the second problem. What this problem says: determine whether the following maps F on K vector space. K is just field. You can, for your convenience, you can consider K is either real number or complex number. Sometimes it is considered as a finite field, but mostly the linear algebra situation, it is either real or complex field. Okay, or sometimes it goes to the rational field. But you can do real and you can consider real and complex. Okay. Determine whether the following maps F on the K vector space Ck alpha. What is Ck infinity? That I infinitely differentiable functions K valued function. If I, instead of infinity, if we had n, then n times differentiable, continuous and differentiable. I think continuously differentiable. And if I have infinity, that means infinitely many times differentiable K valued function. This is what it is value. This is what is the number of differentiability. Infinitely many times differentiable K valued function. Okay, defined on the interval I. Defined on the interval I. This is what it is, the interval presence. Okay, that's the domain of the function. Okay, so this is what it is, C alpha, and the question is into itself. So this is the space. So let's take f is a function which maps C infinity I to Ck infinity I. Okay, infinitely differentiable K valued functions defined on the interval I. Then we have to check whether f is linear or not. If a is given by f of x is a function right now. X is not a value. X is function right now. F of x is equals to a x to the power n. This is nth derivative of the function x. Okay, plus a1 x dash. This is the first derivative plus a naught x plus b. We have this for some fixed an minus 1 all the way a naught comma b. They are also function, just they are also not scalar. Here x dash a b a1, all of them, none of them are value, they are just function. Okay, function defined on the interval I and infinitely differentiable. Question is whether f is a linear map or not. So let's check. There is another way. There is an if it is linear, then what we have to, if it is linear, then for any x and y coming from the space C alpha k and C. I can't write C. Yeah, I can write. That's okay. Let's write C coming from the field. What is the field here? Field is actually K. Okay, this is the field. Okay, then we should have f of cx plus y is equals to c of f of x, f of y. So what will happen? F of cx plus y, that will be that means what is f of cx plus y? C is scalar. You know, C is coming from the field. X and y are function. What will be? That will be a n cx plus y whole nth derivative plus a n minus 1 cx plus y whole n minus 1 derivative all the way a1 cx plus y its first derivative plus the term is that a naught cx plus y plus b. B is itself is a function. Okay, Note that differentiability is actually a linear map. Note that differential operator is a linear map. Linear function you can write, linear function. Why? That is like f of, if I take d is the differential operator, b of some f plus g. What we know? That is, this is df, differentiation of the function f, plus differentiation of the function g. This is what is called the linearity of the differential operator. Similarly, integration is also linear operator. Okay. Operator and linear transformation are the same. Whenever we are considering linear transformation over the same vector space, the initial and the target vector space both are same. In that situation, linear transformation sometimes called linear operator. Okay, but they actually same. They don't have any separation, at least for the context, whatever we are doing in that context. Okay, so here we have differentiation operator. So as single differential is this way, then what will happen? dn f plus g, nth derivative, that is also going to be same way, right? There is no problem with this. Okay, so from here what will get? I will get an c xn plus an yn. Next I will get, this is the corresponding to the first term. Next I will get c an minus 1 x n minus 1 plus a n minus 1 y n minus 1 plus all the way. In this way, if I proceed, then I will have a c of a x dash plus a1 of y. Next one is a naught cx. I can write c of a naught x plus y plus b. This is what it is. Now we can write this as c of an xn plus a n minus 1 xn minus 1 all the way c of c I have taken common a1 x dash plus a naught x plus b plus I can write an yn plus a n minus 1 y n minus 1 all the way. I can write a1y plus y plus b minus b. So what I'll have c of, this is f of x plus f of y minus b. So if I look at carefully that from here to here, what is we are getting? We are getting an extra minus b. Okay, we are getting an extra minus b. So if it is linear, if the function f is linear transformation, then this entry should not happen. This should not appear. So this entry should not appear means this entry is 0. If this entry non-zero, then f is not a linear transformation. So from here, what we can say, f is a linear transformation if and only if b is equals to 0. Note that if b is not equals to 0, then you can say that okay, you can find any x and y for which you will have this not equals to can happen. You just can take x and y two function for which you have this happens. X, let's take x square, and y is, let's take y square. For these two function you can get this situation that this equality does not happen. But if b is equals to 0, then this is linear, that I have proved. Okay, so if it is linear transformation if and only if b is equals to 0, this is what it is. So this settles the first question. What was the first question? First question is that if we have f look like this, then whether it is linear or not. So this linear if and only satisfying this condition. Note that here it is the second function. I have said this is x dash square, that is double derivative and square. Whenever there is square, that is not a linear transformation. This x square, this is itself is not a linear transformation. Why? So just give you the, let's take f is the function from that c k infinity I to c k infinity I. And let's take, given that x is equals to x square plus x dash square. I can show you individually for all of them this is not a linear transformation, and plus addition also going to be not a linear transformation. Why? Let's see. If we just have the function f1x is equals to x square, then you can say that's not a linear transformation. Why? Because if you take let's take function two function that x1 is equals to the polynomial t in t, and x2 is equals to constant polynomial 1. Then f1 of x1 plus x2, that is equals to 1 plus t, and that is supposed to be 1 plus t square, that is equals to 1 plus 2t plus t square. But f of 1 of x1 plus f of x2, what it will be, that has to be t square plus 1. So we that these two are of course not equal. These two are not equal. Okay, these two are of course not equal. So that means this function individually is not a linear transformation. Similarly, if we consider f of x equals to x dash square, this is not x double dash. That means we'll do the derivative and then take square. Then it is not a linear transformation. Note that we have mentioned any order of derivative, that itself is a linear transformation. But if we take derivative and then square, then that is not a linear transformation. Why? You can take the same example here, that t and 1, then what it will have, that if you take the same example, then f of 1 plus t, that will be 1 plus t dash and its square. What is 1 plus t is dash? First derivative of 1 plus t, that is 1, 1 square is 1. And what is f of 1 plus f of t? That is f of t, that is equals to 0, f of 1 is equals to 0, f of t is equals to, okay, this situation it is happening. So I have to take different examples. So let's take t square. Then what it will happen, it will be 1 plus t square. Oh no, I have written little that example will work. Okay, let me give you the example. 1 f of 1 plus t, okay, that is equals to 1 plus, okay, no, that example is not going to happen. Okay, so if I take 1 plus t square f of, that will be 1 plus t square, its derivative d dt, and its square. What is d dt? That is 2t, right? 2t square is equals to 4t square. Similarly, if I write f of 1, similarly if I want to calculate this function, similarly if I calculate this function f of 1 plus f of t square, what it will be? It will be first f of 1, that is the first derivative of entry 1, that is 0, and that square is 0 again, plus 2t plus, I think I'm doing a little mistake. Okay, let's take t. This will be 1 plus 2t square, that is equals to 1 plus 4t plus 4t square. Then it will be t, that will be 1 first derivative and its square, that is 1 again, plus first derivative, that is 2t, and its square 4t square. So clearly these two are not equal. So this happens that 1 plus 4t square is not equals to 1 plus 4t plus 4t square, that is f of x f2. If I write f2 is equals to this f2, this is write as a f2, then f2x is not f2x plus y, f2t plus t square is not equals to f2t plus f t square, and you can sum you can do, and then you will check that this is, and this is also not linear. Similarly you can check not linear, not, I mean individually this is not linear, but individually not linear does not saying you that some can be linear, some cannot be linear. That I don't know, at least no, that does not guarantee. If we have two individual operator and one of them are not linear and another is linear, both of them are not linear, then their sum can be linear. But in this situation it is not linear. For example, here in this example, here we have b. This is a linear, this is a function. Let's take another function f of x, which will be as same with the first entries, and the last entry will be minus b. Okay, in that situation, if I take that like this is f2, this f1 f2, that will cancel out bb. But if we know that if there is no b, then the function has to be linear. So that means f1 plus f2 in that situation will be linear, but individually they are not linear. So that's what I'm saying, that when I'm proving that here it is that individually x square and x dash square, that is not linear, that does not guarantee that their sum is called cannot be linear. But in this situation, it cannot be linear. Okay, that you can check. Okay, so I will not do any more problem in this linearity. I mean, in these questions, the other one you can check by yourself. Let's go to next problem. Okay, before just one few seconds, I'll check. Yeah, so let's go to the next problem. If you have any doubt or anything you are not able to understand clearly, you can ask me. I will try to discuss those things. Let's go to another problem. What was the problem? These are the assignment problems which are you are supposed to practice. Those problems I am discussing. So here what is given, that let D is a subset of K and P not be a fixed point. Then substitution homomorphism is a K-linear form on the K vector space of all K valued function on D. Okay. So what we know, KD is nothing but the space of all function D to K. Okay, this is already KD. K is a field, we know, and D is a subset of K, and T naught is one of the point inside D. So here the transformation is that E T naught that maps the function KD is a vector space to the K that sends E T naught that maps F is a function from D to K. Okay, that is given by F of T naught. Because F is a function from D to K, so and T naught is a point inside D, then F of T naught is an element inside K. There is no problem with this. This is a well-defined map. So this says this is a well-defined map. This epsilon T naught is an well-defined map. Well-defined map. But I have to prove this is linear transformation or not, right? Or it is given. Then the substitution homomorphism is a K-linear map from K-linear form, because whenever linear maps taking the value on the field, then that is called form. Okay, form on K vector space, on a K vector space of all K valued function on D, its kernel is the function. What is kernel? I am coming to this, but let's first check whether this is K linear or not. So if I take two functions f and g coming from KD, that is the function from D to K, then by the formula ft naught f plus g, that has to be equals to f plus g at the point t naught, that we know by very simple formula, that is g of t naught, and that we can write epsilon t naught at the point a plus epsilon t naught at the point g. So if P is a linear transformation, so this is linear, so that means this says epsilon t naught is linear transformation, and whenever transformation here, whenever the vector space W is taking the value, W is nothing but the field itself, because if V is a vector space over the field K, then the field K itself is a vector space over himself K. Okay, over itself K. Okay, so that's why what I'm saying, that if V is a vector space over the field K, K itself is a vector space over itself K. Okay, so that's why but whenever W is K, when you choose W as K, in that situation this is called form. Okay, this is a linear form. That is what it is proved. But what I'm going to give you right now, I'm going to give you what is the kernel of a linear transformation. Let V to T from V to W be a linear transformation. then kernel of T that is equals to all those vector space coming from the vector space V such that TV is equals to 0. Okay. First of all, this is a fact. This is a fact. Is a subspace of V. Second fact, T is injective if and only if kernel of T is actually nothing but contains 0. Because if T is injective, then TV equals to 0 implies V has to be 0. That means this set should not contain more than other entries. And if kernel of TV equals to 0, that means all the entries V in capital V for which TV equals to 0. That means V has to be 0. Okay, so that means T is injective. I hope this is not very difficult. This is not very difficult. If T is injective, if and only if kernel T is 0. Still, if you have doubt, you can ask me. I'll try to discuss. Okay, but let's calculate what is the kernel. Kernel is, so what is the kernel of this? Question is, what is the kernel of epsilon T naught, which is mapped from KD to K. Epsilon kernel of T is equals to, kernel of epsilon T is equals to all those function f from D to K such that f of T naught equals to 0. That is what it is, right? That is equals to, if I just more explicitly, if I write epsilon T naught at the point f equals to 0, that is nothing but all the function from D to K for which f of T naught equals to 0. Note that when a function, when the collection of all function which vanishes at some fixed point, that is always a subspace. Because if f and g, two function which vanishes at the point T naught, then CF plus G, C is a scalar, that at the point T naught, that should also vanish. That means if F and G are there and C is a scalar, CF plus CG, CF plus G also will be there. So this is very easy way that when this is a subspace or not. Okay. So that's why if you remember, so that means what I have said, if you are taking a collection of functions which vanishes at some fixed point, that becoming a subspace, that is true. And in fact, by vice versa, you can say something like that. Let's take you have a vector space R2. This is something different from the question. I'm coming back to question once again, but let's be here. We have the vector space R2, and we are taking the space of all functions from R2 to R. There is two vector space. This is a vector space R2, and I'm taking space of all functions V2. That is equals to all functions from R2 to R2. Then if we fixed a vector x belongs to R2, then the collection of all function from R2 to R2 which vanishes at the point 0, that is a subspace. On the other hand, if f is a function from R2 to R, all the x belongs to R square for which f of x is equals to 0, that is again a subspace. But here we need f is linear. Okay, without that we can't say anything. But to become this subspace, to become subspace, it is sufficient that f is linear. Okay, this is something off the line. Okay, so this is what it is. We have proved that kernel of epsilon t is equals to all the x belongs to kd such that x t not equals to 0. Okay, so I hope this is all. So let's go to the next problem. So this is what it is we have done. So here is a problem, another problem. So what this problem says, let's I be a subset of R. This is interval with more than 1 point. 1 point should be there. Okay. Then the differentiation defines a k-linear map. Okay, what is ck1i? ck1i is all the continuously differentiable function, and ck0i all the continuous functions. All of them are defined on the interval I and taking value on the field k. Okay. So ck1i continuously differentiable k-valued function defined on I, and C naught k I continuous k-valued k-valued function defined on the interval I. So what is we mean by continuously differentiable? Continuously differentiable means if we take derivative, derivative will be continuous. That's what it is. But derivative has to be differentiable or not, that we don't know. Okay. So here is a map. Map is that D is the map. That is the differential map. CK1 I to CK0 I. That maps every entry to the derivative. So right now, as we have said, the CK1I consists all those function which is differentiable and derivative is continuous. So that's why x dash is continuous. That's why x dash is belongs to this. So this is well defined map. There is no problem. But the question is, we have to prove that then D is surjective. Then D is surjective since every continuous function, a primitive or antiderivative function exists. Okay, what is the antiderivative? So prove that. To prove D is surjective. So here let T naught is a fixed vector coming from the interval I. I have more than two elements. That's what it is mentioned. More than one point. More than one point. Sorry. T naught is one of the point. There must be other point. Okay. I'm coming to that point. Now, if I define a function x at the point t, x is a function from I to, or define, I can write define x from I to the field k by x of t is equal to integration over t naught to t x of u du. This is just usual integration. Okay, as the function is continuous, that has to be integrable. There is no problem with this. Okay, what is the question mark 6 5? As the function is differentiable, it has integration. There is no problem with this. But by the fundamental property of, by the fundamental theorem of calculus, dx dt, that has to be equals to, here I have to take x dash, that has to be equals to x dash. This is what it is. Or I can start with something like that. Surjective. Let t naught belongs to this, full stop, and let y is a function coming from ck0 I. That means y is a continuous function. Then I want to define a new function, that is x, defined by this way. Then its derivative is actually by by the fundamental theorem of calculus, that has to be equals to y. Okay, that's what it is. Y of t. Okay, let me give you this precise statement of fundamental theorem of calculus. Let me fundamental theorem of calculus. Let me write the precise statement. What this says, fundamental theorem of calculus. Yeah. So if f is continuous, but here I think we have considered a real. Here it is real. If it is a continuous real valued function, then only, okay. Fundamental theorem for calculus for real here only. Let f be a continuous real valued function defined on a closed interval AB, then the function, if I define like this way, f of x is equals to a to x f of t dt, where x is coming from the interval AB, of course. Then f is uniformly continuous, and f is differentiable, uniformly continuous, then it will be differentiable, but f dash is equals to, there is some other term like f is uniformly continuous and differentiable, then f is different, f is, let me write them, f is uniformly continuous and differentiable on uniformly continuous on the interval AB, close interval AB, and differentiable on AB. Okay, this is what it is, and this happens. Okay, this is the fundamental theorem. That is what it is. I have applied there. Okay, this is what it is. So that means we have for every y in C naught k, we have a function xt whose image is under is this, that is equals to d of x. Okay, so that this says f is surjective. This says d is surjective. But whether d is injective or not. So d will be injective if and only if the kernel is 0. But let's calculate kernel. What is the kernel? Kernel of the map T, that is equals to all those function which is coming from ck1 continuously differentiable function over the interval I, such that derivative is equals to 0. Okay, this is what it is. So that which function has derivative equals to 0? But okay, here is the interesting fact. But question is, the derivative equals to 0, identically 0. The derivative 0 means, but which continuously differentiable function differentiable function has derivative 0? Always 0, right? This is what it is differentiable. Why? Which continuously differentiable function has derivative 0? So here is, I'll use the mean value property, mean value theorem. What the mean value theorem says? If here I is an interval, note that if f from a b to r be a function which is differentiable, which is continuous on AB, close interval AB, and differentiable on open interval AB. Okay, let me write it clearly. Differentiable on open interval AB. In that situation, there exists a point C coming from the open interval AB such that f dash C, that has to be equals to f of B minus f of A by B minus A. So here the one fact where it is using is that it has more than 2 points. Whenever it has more than 2 points, then their B and A cannot be equal. Whenever B and A cannot be equal, as B and A cannot be equal, in the situation B minus A is non-zero, then this is defined. This is what it is main point. So I will use this. So here whatever it says that f of dash is equals to 0. Okay, that means then for any two point A B coming from the interval I, what we get there exists a point C belongs to the open interval AB such that f of f dash C or x dash C, that is 0 by definition, and that has to be equals to xb minus xa by b minus a. Okay, b and a 2 point. I have taken b and a are two separate point. Okay, so that gives xb is equals to xa. But note that here a and b, and I have taken a not equals to b. I have taken two element a and b, and they are not equal. So that means what if, for any, so that means for any two arbitrary point, for any two arbitrary point a and b coming from the interval I, xb is equals to xxa. That happens, that says x is a constant function. So what we have learned today, that continuously differentiable function whose derivative is identically zero, that is nothing but the constant function. F is a constant function. So what we obtain, kernel of D is equals to all those x belongs to coming from C, K, 1, interval I, such that x is a constant function. So that means this is not equals to 0. That says D is not injective. Okay, I wanted to do one more problem regarding this. Regarding this means regarding this integration. There is another problem which involves the integration, but I hope I don't have much time. So let's go to those important points, the problems. That's this color problem. I hope this color problem is supposed to. Okay, okay, just a minute. Okay, so these are supposed to not. These are not supposed to submit. Blue color column are needs to submit. So we can discuss this problem. Okay. So what this problem says that the pollen. Oh, sorry, I have read wrong question. Yeah, this is the question. This is very interesting questions. I hope. Okay. So let's start this problem. What this problem says: let W be coming from positive non-zero real number. This is what it is mean by R plus cross. Positive non-zero real number R plus cross set of all positive real numbers. That is non-zero. Positive means there is no zero. Let W be a fixed. I can't remember whether we have discussed this problem in last class. And let W be the subspace which are the space of all functions f f such that f of f is a function from real to real that given by f of f is at the point t is equals to a sine is equals to a sine w2 plus phi. This is what it is for some a and phi coming from the r plus r. Okay, so a can be 0 as well and phi can be 0 as well, but w is fixed, that is coming, that is non-zero positive. Okay, then we have discussed last day, this is a vector space. Then we have discussed, let me quickly, then W is a vector space. Why this is? Because if we write f of a phi at the point t, W is fixed, okay? That is a sine W2 plus phi, that is equals to a sine W2 WT plus cos phi plus a cos WT sine phi. So that means we can write here p is the variable, phi is not, phi is fixed corresponding to a fixed function. So that means what I'm getting here, a cos phi times sine WT plus a sine phi times cos WT. This is the linear combination that is contained in span of two functions. Sine WT, this is the function, plus cos wt. This is the function. Let's take this is s, this is c, sine and cosine, not plus. This is span. Span means this is what it is. So I okay. So this is there, and it is very much true that if we take w is a non-zero number, in that situation, psi wt and cos wt is it is you can check that sin wt function as a function of t and cos wt as a function of t are linearly independent. Linearly independent. How to check that? If you take something like that, gamma 1 sin wt plus gamma 2 cos wt equals to 0, we have to prove that gamma 1 gamma 2 equals to 0, right? So for how to do that, let's take t is equals to 0. So if I take t equals to 0, that gamma 1 sin 0 value, I know that is 0. But cos 0 is 1. So that is going to be 0, that gamma 2 equals to 0. If I take t is equals to 2 pi by w, not 2 pi, where sine is becoming non-zero, 1 basically, but cos becomes 0, that is pi by 2. If I take t is equals to pi by 2 w, w is non-zero, so that's why I can write that one. So then what I'll get, sine of t means that will be sine of pi by 2, so that will be gamma 1 sine pi by 2 plus gamma 2 cos pi by 2, that is equal to 0. We know cos pi by 2 is automatically 0, sin pi by 2 is not equal to 0. This gives gamma equal to 0. So this gives that, all these things gives that sin wt and cos wt are linearly independent. So this is linearly independent, and this every function f a alpha f e that's contained in the spanning set of this set. Conversely, if we take any linear combination of these vectors like alpha sin wt plus beta cos wt, then we can get that can be written in terms of f of a phi of t. That I can write. This form I can write. Then what is the a? That means the spanning set is also contained in the vector space W. That is what it is. Okay. What we can write that here a will be alpha square plus beta square, square root of this, and phi will be what will be? Let me write, if alpha is equals to this, then alpha can be written as then what will get, that alpha square by alpha by a square plus beta by a square, that is equals to 1. That means we'll get some phi for which cos phi, their existent phi belongs to 0 to 2 pi, such that 0 to 2 pi, such that cos phi is equals to alpha by this square plus sin phi square is equals to 1. That is cos phi is equals to alpha by a and sin phi is equals to beta by a. That will give alpha is equals to a cos phi and beta is equals to a sin phi. So that means, but we need that a has to be not equals to 0. If a is equals to 0, that is automatically there. There is no point. But that says that, okay, I can write, then in that situation I can write this entry as is equals to f of a phi, where a is equals to that and phi is equals to this. And what is phi here? Actually, we know what is phi here. Phi is equals to cos sine tan inverse of beta by alpha mod of, right? This is what it is, phi. Okay, so basically what I am saying that the vector space W, which is actually consists of f alpha beta, f alpha phi, where alpha and phi are coming from the real number, is same with the spanning set of sin wt and cos wt. This is what it is, and they are linearly independent. That is the basis. Okay, let's go back to the question. This is not the question. Question is here. That will give the thing. So question is, let gamma be a map W to C, where it is mapping gamma mapping f of alpha phi function to the value alpha a of I phi, where a is greater than 0. This is not alpha. This is sorry. Let me a phi. Yeah, a not alpha. Sorry, a phi, that is going a e to the power I phi. That is the map. First of all, how this map is defining? Yeah, there is a very hidden structure. So, if you look at carefully, f of alpha a phi as a map, as a function, what it is? It is a cos phi. What it is we have discussed till now? Cos phi sine wt plus b cos phi cos wt. This is right, and this is equals to, that means we have this here. I can write here. It is, this can be right. We know e to the power I phi equals to cos phi plus I sin phi, right? So that means gamma is mapping this entry to here and this entry to here. So this is also here, not here. This is it. So note that here we have, proved. Note that we have proved that this set sin wt cos wt is a basis of the vector space W, that is the collection of all functions. Now let's take a linear transformation from W to C to R2. Basically not R2, this is complex number basically. That's sending T of sin W2 is equals to 1 and T of C, here I can just say, here note that W is a vector space over the field R. W is a vector space over the field R, space of all real numbers. Okay, not the. Okay, let me be a little slow and try to read this. I hope I'm becoming. Recall that W is a vector space over R. Okay, C as a vector space, complex numbers, vector space over R must have dimension, has dimension 2 and 1 comma I is the square root of -1. Okay, this is a basis of C over R. Be careful, I am considering complex number space as the vector space over R. Okay, so you should not be confused or should not be mixed. That's what it is I want to say. Okay, so this is a vector space in dimension 2. So now C considering as a vector space over R. So now let's take gamma. Let's take T as a map from the W. W is the vector space of all those functions. W to C over R. Point. This is very crucial. Over R. That maps. If that maps sin WT is equals to 1 and T maps cos WT is equals to iota, then we know this is mapping, and this is two W and C. W is two-dimensional vector space that we discussed, because there is a basis sin WT and cos WT that is consists two entries and they are linearly independent. So two-dimensional vector space, and C also two-dimensional vector space over R. So T is a linear transformation that sends basis to basis, that is T is a bijective linear transformation. I mean, linear means, how linear? Okay, here is the interesting fact which I have started, that if we have a linear transformation, then it is enough to know the values of the linear transformation only on a single basis. Then for any entry in W, what will be the any entry in W? Any entry in W is like sin W2 plus beta cos WT for some alpha beta coming from a real number, because that is what is the things. Then T of the linear transformation T is nothing but alpha of T sin W2 plus beta of T cos WT. Okay, this is what is the function. So now alpha beta, for some alpha beta belongs to real number. This is the arbitrary element. Arbitrary element in W look like this way, that I have proved also. And T makes the map which should be look like this. So that's the linearity. That's using the linearity, because I want to define a linear map. So what I have said here, actually, if you are giving a function whose values are given on a basis of a linear vector space, then you can define a linear map on the full vector space. How to define? This way. Arbitrary element in the vector space V is look like this way. Now if I write T, it look like this way, that alpha of T sine, because we know this, what is this? We know what is this. Then we know alpha of this sum plus beta of this sum, we know what is this, right? So that way one can define the linear transformation if you know only the values of the linear transformation on a basis. This is very interesting now. So this uses the fact that, let me write, it is important to note that, important to note that this is already I have said some other form, that if a map is given only on a basis of a vector space, then one can generate a full map on that full linear transformation, not just a map, linear transformation. Not just because if you just if you want to get a map, you can just map every other entry to 0. That you can do, but that's not the linear map. One one can generate a full linear map. One can generate a linear map on that vector space using those values. Okay, so this is a linear transformation and this is bijective. Main point is that T is bijective because T maps basis to basis, two-dimensional, which is bijective. So why I am going to say T is bijective? Here I want to come here. So let's, gamma is the map. This is same map. See, gamma maps A cos phi sin W2, this is the function, plus A sin phi cos W2, that goes to A cos phi plus I of that same map, the T. Okay, how I can say this is the same map of T. Okay, basically this is same map. Okay, let me write this, I of sin I of A sin phi. So that nothing but A cos phi T of sin WT, because that is 1, plus I A sin phi. This is I will be replaced by T of cos WT. That goes, T is linear map, the A cos phi sin WT plus a sin phi cos WT. So that means here it is one fact we are getting. So that says T is equal to gamma. Here is one fact I am using. I mean, I am ultimately proving that if you have two linear transformation, they agrees on a basis, then they must be same. If we have two linear transformation on a vector space, on a vector space such that they agrees on a basis common basis, of course, common basis of V, then these two linear map must be same. So why I am proving all this drama I am doing? Just this is just this two same. So that means T and gamma are basically same. So what is the question? Let's get back to the questions. Question is that this is an isomorphism you want to see. That's true. That's true. Because T is an isomorphism. Because T maps basis to basis. And gamma and T are same linear transformation. So that's why as T is isomorphism, gamma is isomorphism, because they're same. is R vector space isomorphism. That's very important. That's what it is I'm trying to mention here. That whenever I'm considering this, here I mentioned somewhere that over R. So thus gamma is an R vector space isomorphism. Okay, and this is one of the problems. So let's go to the another problem. I hope that will be enough for the day. I don't know how much I will be. Okay, so before going to this, let me first see the problem. If that problem is bigger, then I will not going to discuss today. No, that problem I hope is not bigger. At least few percent can be done. Okay, the problem I need to write in hand. That's the problem. Another problem. So what the problem says? Let I is subset of R be an interval with more than one point, and let A belongs to I full stop. For n belongs to capital N, let TAN, that is the map, that is k valued n minus 1 continuously differentiable defined on interval I to KTN, that is polynomial of degree n, be the map which maps every function if, that is n minus 1 times differentiable k valued function defined on I to its Taylor coefficients, Taylor polynomials of degree. So that means this is a polynomial of degree less than n. Okay, degree n of f at a, that is the function f is mapping to P of a n f is equals to summation of k equals to 0 to n minus 1 f k e by k factorial p minus a whole to the power k. Question is, this is what it is. Question is, so that PAN is R linear, K linear. This is the first fact. Determine the kernel and the image of the. I think I will do one either kernel or image. So, and the image of the map. So this is what it is I have to do. Okay. So you have to find the T map. You have to find the kernel and image of the map. Okay. So before that, let me just formally mention what is KTN means. KTN is defined many times, but still I hope um, polynomials of degree less than n. There is a basis 1 p minus a. If a is a fixed number, then okay. Let considering them, we can consider this polynomial considering them as function on the interval I, which contains more than two elements. Let a belongs to I. Then these are the common fact which I have mentioned many times. T minus, not many times, at least once I can say. T minus a whole to the power n minus 1 is a basis KTN. This is the basis. So the map T A n, that is from C n minus 1 K I goes to C, sorry, not C, that's the KTN. That's sending every element to the polynomial. So that's sending TAN at function to the Taylor series expansion. That is equals to K equals to 0 to n minus 1 f k a by k factorial t minus 1 whole to the power n. So question is, it is linear or not? So it is linear. Why it is linear? T of a n, a plus g. If I just, I'm not giving the scalar, but you can understand this is scalar is there. So then it will be by definition n equals to 1 to n minus 1. So for any c coming from the field k, fg coming from this, say this space, we get this is equals to cf plus g whole k factorial into t minus a whole to the power n. As we have said very early that differential operator is a linear operator, okay, but not their power. So here it is differential operator, k time differential operator. So you can directly write c of n equals to. If there is any doubt regarding this direct step, you can ask me. I will try to then explain in more details because I am assuming this may be easy to understand. If even it does not feel, if it even does not feel it is easy, then you can ask me. I'll try to discuss. GK GKA by k factorial t minus a whole to the power n. So that means C of t a n f plus t a n g. Okay, that's all. So this is linear. So this says the map Tn is R linear. R linear, right? K linear, not R linear, K linear. K linear. But the main point is that what is the surjectivity? So let's check surjectivity. Here the map will be surjective, not surjectivity of Pn. So let's take polynomial P is coming from K Tn. That means P can be written as from A naught plus A1 T minus A plus all the way A n minus 1 T minus A whole to the power n minus 1. Right? Here it is, you can write. Now, interestingly, how one can get a function? Question is, what is the function if belongs to the c k minus c n minus 1 k interval I such that t a n f is equals to p. That is nothing different. So p is, if this is a polynomial, we know for any polynomial can be written in the form that p naught, this is p naught, this is p dashed a, this is not p naught, this is p a, p dashed a by this t minus a plus p double dashed a by 2 factorial t minus a square. You can check easily. That is you can check. If you just, for example, if you just replace p at t, this is the of course p at t, p of a. What is this? A naught. That's what it is. Here it is. Okay. Let's take its derivative. Let's take its derivative. If I do first derivative, what I will get? I will get a1 plus a2 into t minus a. All the way last one will be a n minus 1 into n minus 1 times t minus a whole to the power n minus 2. Now just let's replace t equals to a again. Then what I will get? A1 is equals to p dash a, right? And check. This is, you can check carefully. Okay, so this is what it is. Similarly, we will get the other one, and that way what we'll get at the final term will be nth derivative by n minus 1 whole factorial into, okay, here I am writing, n minus 1 derivative, so this is the first position, yeah, n minus 1 derivative by n minus 1 factorial at the point a into t minus a whole to the power n minus 1. This is what it is. So what I'm getting, the function, if for which this happens, the function f is nothing but p of a p dash a t minus a plus all the way p n minus 1 derivative of a by n minus 1 derivative of a t minus a whole to the power n minus 1. If I consider f is a function over the interval I to the field k, where f of t is equals to look like this way, then this is very much clear. Its Taylor coefficient, Taylor polynomial is corresponding Taylor polynomial is p. That's very much clear. If there is doubt, still you can ask. So this will give f is surjective. Why this is happening? This is very standard theorem. If you have a polynomial, what is Taylor polynomial things are doing? If you have a function, it is considered that it is not considered. It is something assumed or something standard that polynomials are well understood things because they have finite degree. But if you are not a polynomial but some other function like exponential function, sin x function, cos x function, trigonometric function, all other type of function, logarithmic function, all these functions are not that much well understood or well, we can't compute those functions very easily. Polynomials are very easily one can compute. So that's why when you have a function which is not polynomial, then what one wants to do find the Taylor series expansion, because that looks like a polynomial. Okay, that gives an estimation of the function. So that's why whenever you have already that polynomial, then Taylor series expansion of that polynomial will be itself. So that means if you have a polynomial, if you want to get the corresponding function, that function is itself the polynomial. Okay, so that says p is p of an is surjective. Okay, but the injective thing. Now the injective thing. Note that t an is injective if t of f is equals to 0. T of an f is equals to t of an f is equals to 0. But this is a polynomial. Polynomial of the form f of a plus f dash a by f dash a into t minus a plus f double dash a by 2 factorial into t minus a whole square plus all the way t f nth minus 1th derivative at the a by n minus 1 factorial t minus l to the power n, this is equal to 0, right? But a polynomial is 0 polynomial, then each of the coefficient of this polynomial, each of the coefficient of this polynomial must be 0, because this is a polynomial of finite degree. Okay, as the polynomial is of finite degree, as the polynomial is of finite degree, so it can have only finitely many distinct roots. It can have only finitely many distinct root. But here a polynomial is 0, that means it is 0 for every point. Now if I is an interval which has many points, if you have two distinct points, there is an uncountable number of points inside I. But here it is saying this polynomial is 0 at all the point of that interval. That means it is uncountably many points is there, but the function is becoming uncountable many points is there where the polynomial is becoming 0. But the polynomial that is Taylor polynomial of a is 0 on I, which contains uncountable many points, because there is two distinct points. There is two distinct points. That means there is an infinite number of points inside that, because this is interval. If two distinct point is there, interval, that full interval will be, sub interval should be there, right? So this is what is the region. So that means f of a is equals to 0. That has to be f of dash a has to be 0. All the way f of n minus 1 a has to be 0. So that says kernel of TAN, that is equals to all those functions coming from the C n minus 1th differentiable k valued function defined on the interval such that f of a equals to 0, f of dash a is equals to 0, all the way f of n minus 1 derivative is 0. This is what it is, the kernel. Okay. So what we have obtained here, that function is surjective, TAN is surjective, but it is not injective. And that's very obvious. Why this is obvious? Because whenever we are taking all this n minus 1th differentiable k value function defined on the interval I, that automatically contains the polynomial as a function over the interval I. Polynomial, whenever I'm considering polynomial, that's in general not considered as function. But if we consider it as a function over the interval I, that means t is taking value on the interval I. In that situation, this set is actually nothing but contained there. So if that set is contained there, and you want to give a map from here to here, that means corresponding to each entry here, you will get an entry here. That's what it is, we are doing surjectivity. But it's not very natural that for every entry here, you will get an entry here. That's not very natural, right? If a set A is contained in B, and you are giving a map from B to A, that means for every entry from here, you will get a map entry here. That's it is possible, right? That's it is surjectivity. But for every entry in B, you will not get the all. You will, I mean, for every distinct entry in B, you will get distinct entry in A. That's not possible, because whatever the entry which is not in A, those entry has to map 0. They can't map anywhere else. They has to map 0. If I want to give a map A from B to A, and the mapping entries A to A for all A belongs to capital A, then where it will go? If B belongs to A, this is B, and if 0, if B is not in A, but some 0 entries there, something like that, not in A, there is no other way one can map, right? This is roughly. So main point is that this is the question. So I hope this is clear. So TA is not injective. This is not 0. So this is all. I hope this is all for today. So if you have any query, you can ask me regarding this course content or anything. I think someone asked me about the question pattern, but sorry, I forget to know. I will try to know. I mean, I have not tried to know what is the question pattern, possible question pattern for the end sem. I'll try to know in the next part. There is no guarantee that I will come with an answer. With an answer means with an positive answer. Okay, the faculty may refuse to inform us about the course pattern. Okay, exam pattern. So apart from this, if you have any questions, you can ask. Otherwise, I will close this session for next 1 to 2 minutes, and the next tutorial session will be on the next Friday from 7 p.m. to 9 p.m. Till that point, if you have any query, you can mail me to the mail ID ma21d018@smail.iitm.ac.in. So if you have any questions, you can let me quickly ask. Otherwise, I'll close this session in next few seconds. Okay, I hope there is no question. So let's end this session for today. We'll meet in the next Friday, 7 p.m. to 9 p.m.